Thanks, everyone. Wasn't that awesome? Man, that was like everything that I wanted to do in a talk, and I kind of wish I could go and rewrite this entire thing. By the way, there are WebAssembly Nintendo emulators, so you probably incorporate the two, don't have to download it, play from the web. It would be very, very, very cool. I probably should talk afterwards. My name is Ben Smith. I work at Google on the Chrome team, and more specifically on the WebAssembly team. So I'm here to talk a little bit about WebAssembly. Here's the basic layout of the talk. I'm going to talk a little bit about WebAssembly, have a sort of WebAssembly 101. And then I'm going to talk about an example where I'm going to use WebAssembly in Node with a thing called Brotli. And then I'm going to talk about how those things go together, WebAssembly and Node.js. And by the way, for the people who are going to get a little bored, because I do have a lot of assembly, probably more than Rachel did, I drew some little squiggles on the screen, so you can look at those instead. So here's one thing that's very cool. WebAssembly is enabled by default in Node 8 LTS, which means you can use it right now if you're using Node 8. So why would you use it, though? What's the purpose of it? Well, we'll get back to that. First, I kind of want to give you an idea of what it is. So WebAssembly is this project that a number of browsers, we got together and we started talking about, like, well, what if we had a different execution engine that wasn't JavaScript? We love JavaScript. There's a lot of great things about JavaScript. I mean, this is a JavaScript conference. I'm not going to say JavaScript is, it's great, it's awesome. But it does have some things that are maybe not exactly what you would want, like, and I'll get into some of that later. And so we started to talk as a group, and recently, earlier this year, we launched WebAssembly in Chrome and Firefox, and very recently, Safari 11 and Edge, Chakra Core, also support WebAssembly. So we're very, very excited about this. This is actually kind of one of these things that doesn't really happen on the web, which is kind of sad, but like everybody getting together and saying, OK, well, let's all launch it together. So we're very, very excited about this. We have a community group where we come up with new ideas that we can add to the language. And we also have this GitHub site where basically anybody can contribute. We do all of our work out in the open in terms of the spec. We have a reference interpreter so that you can run WebAssembly and see what it looks like, and so on. So this is what webassembly.org says WebAssembly is. And I kind of like this quote, and I kind of don't like this quote. And the problem with this quote is that it's like, you look at it and you're like, so wait, what's the noun? What's the actual thing that it is, right? New portable size and loaded time efficient format suitable for, oh, it's format. You're like, well, what does that mean? Well, so I'll break it down in a second, but the way I like to think of it is that it's an executable format, like JavaScript, but it's primarily a binary format, and that's really important. The reason why we wanted it to be a binary format is so that it could be size and load time efficient. So I'm going to go through the words here. So when we say portable, we mean portable in the same way that JavaScript is portable. You expect it to basically run everywhere. Earlier talk from Gordon about Espruino, it's running on microcontrollers. It runs everywhere. Well, we wanted to have a similar goal. Like, if WebAssembly is going to be on the web, it needs to be able to run everywhere. And so that means it should be able to run on any number of different OSs, any number of different ISAs, and any number of different JavaScript engines as well, and non-JavaScript engines. So I've listed JavaScript engines up here, but there are a number of people who have been implementing their own non-web implementations. We actually like the idea that it's simple enough that, one developer can write their own interpreter, write their own JIT, even if they want to. So that's very, very cool. It's also size and load time efficient. So what we found was that minified JavaScript is actually quite small, but you can do better in terms of size. So what we focused on was trying to make it so that we had a format that was small, but also compressible. Another benefit is that JavaScript is actually kind of a difficult language to parse. I mean, not particularly difficult. It's not like C++ or anything, which is notoriously difficult to parse. But it's not as easy as it could be. And so one of the things we wanted to do with WebAssembly is make it so that it was fast to parse and then fast to validate. And I'll talk a little bit about validation later. And then also be able to generate good code quality, like consistent code quality. So that's kind of what size and load time efficient means. And then suitable for compilation, this is kind of the crux. This is the reason we call it WebAssembly. It's actually not a very good name, because it's not really an assembly. It's more like web machine code, but that doesn't really sound as good. So it's meant to be a compilation target. You're not meant to write it by yourself. And when I show you some of the examples, you'll see why. It's very verbose, but that's because it's assembly language. You're not meant to write it. I mean, well, unless it's 6502 and you're super awesome. Currently, the language that we support are C, C++, and Rust. We also have some experimental support for languages like C# and Java. A lot of people are very excited about the opportunity to be able to basically take their language, their preferred language, and compile that and then ship that to the web as a client. And in the future, we're planning to add a number of other languages as well. We'd like to really work with language designers and existing languages so that we can compile to their language, or compile their language to WebAssembly and be able to run that. So if you know anybody, or if you are a person who's like, I'd like to run WebAssembly, please talk to us. Come to the WebAssembly CG, and we'd love to talk. And so, of course, this is a Node conference, but WebAssembly, the original idea was about it being for the web. And so some of the things that are necessary for a website is that it has to be sandboxed. You don't want to run into a situation where you just take an executable and run it on somebody's computer, right? That would be horrible. Like, think of the security issues. So we want to make sure that it's a safe executable, and you can be certain that you run it and it's not going to format your hard drive. Another thing that's super important is that it needs to have synchronous interoperability with JavaScript. I mean, JavaScript is the language of the web, right? And WebAssembly isn't meant to supplant it. So it needs to be able to communicate with JavaScript, all the JavaScript APIs. And that's true for Node as well. And like I said, it's also useful in non-web scenarios, such as Node.js. So when we talk about JavaScript and WebAssembly, this is kind of what people often think. They're like, oh, well, JavaScript and WebAssembly, they're really fighting, right? Like, WebAssembly is going to take over JavaScript. And like, no, this is not how we think of it. I think we think of it more like this. Like, JavaScript and WebAssembly are like in a dance. OK, maybe not like in a dance, but you know what I mean? Like, they work together. They're meant to be used together. Using WebAssembly for what it's good at, and using JavaScript for what it's good at. But I need to talk about some of the differences, and so I had no idea how to draw XOR, so sorry about that. So imagine that you have this JavaScript function, really simple function, right? This is adding two numbers. But is it? I mean, I know you've all seen this kind of code before. It's not just adding two numbers. You can add a string in a number, or an array in a number, or you can add all sorts of different types. And your JavaScript engine has to deal with this. And actually, one of the reasons why JavaScript is, a somewhat difficult language to compile, and my colleague Benedict is probably going to get upset because I'm going to paper over all of the complexities of JavaScript. But one of the things that's difficult about it is that when you write a piece of code in JavaScript, it doesn't really know what the types are for that function yet. And so it has to run a few times, and then it says, oh, well, you're mostly calling with numbers. OK, we'll optimize for numbers. And then once we have that code optimized, we'll check every time you call it to make sure that you're still calling with numbers. And if you ever call it with something that's not a number, then we bail out, and then we do something special. And there's tricks to do that, but it adds some complexity to the code. So this is what WebAssembly looks like. And you can see it's quite a bit more verbose. Another thing you might see is that it has types specified. So the i32 is a 32-bit integer type, and it has specified operations for 32-bit types. So what this is saying is, take a 32-bit number, take another 32-bit number, add them together as parameters. So it's the exact same function, but it's written in WebAssembly. That slide should have been before. But I guess I can say these are the only types that we have. There's a 32-bit integer, there's a 64-bit integer, there's a floating 32-bit float, and a 64-bit float. Also, for people who have been writing JavaScript for a while, the 64-bit float, it's pretty nice. You're going to get it soon. You're going to get it soon. But we have it now. So the cool thing about what we have when we have this limited set of types is that we can do validation on our code. So when you take that code and you compile it and you instantiate it in the browser, what happens is it does a validation pass over the code. And it says, does everything make sense? Do all the types sort of add up in the way that I expect? And if they don't, it won't compile. So what you see here is a call operations. This is the actual call instruction that WebAssembly has. And if you pass it a float, or if you pass it an int64 and an int32, then it says, nope, that looks wrong to me. I don't know what these are. You have to put an explicit cast in. Again, another reason why you probably don't want to write this by hand. It's tedious. But this gives you the benefit of the compiler, the benefit of being able to say, OK, well, I know exactly all the types. So that function, I can turn into one instruction, probably, maybe two. And that's very powerful. It knows exactly what to write there. All right, so let's look at a little bit more complex example. This is a JavaScript function. I don't know if this is how everyone would write it, but OK. So we're going to add up a bunch of values in an array, and then return the result. Really, really simple stuff. So the thing is, in WebAssembly, you don't get arrays and objects and all that other stuff. What you get is one big bag of bytes. It's like an array buffer. We call it linear memory. And so you have to sort of treat memory differently. Again, another reason why you probably don't want to write this by hand. It's a little tedious. So this is a sort of JavaScript version using typed arrays that's a little closer to how you might implement it in WebAssembly. So basically what's happening here is we've got an array of bytes, and then we put values in order, and we have a begin and an end, and that's kind of like our array, right? And then we'll loop through, and we'll access our value, and then we'll add up the results, and then we'll return the answer. And so then you could basically instantiate your U8 array, call your function, pass in your range, and then you get your result, right? Everybody get it? All right. So this is the WebAssembly equivalent of that. It's a little bit nasty, and maybe you can't even read it. I don't know. It's a little small. But I'll go through the pieces and just sort of give you an idea. Again, this is just to sort of give you a flavor of what it looks like. So this first part here, this is the do-while part of the code. So there's a loop at the top, and at the bottom there's like a branch back to the top. It's a conditional branch back to the top. So that's how you sort of represent a loop. And this LTS here, that's the signed less than comparison. I love this stuff. I'm looking at everybody's faces to see if you're paying attention or if you're tuning out at this point. So there's going to be a quiz at the end. This part right here, this is basically doing the result plus equal U8 array begin part. So it's essentially saying set local is like take this local variable and set its value. Then add is saying add these two numbers. Get local is saying get this value. Add to a value that I pulled from the memory. That's what load8 u is. So this is the sort of operations that's actually doing the sum. And then finally, this is the one that's doing the increment. This is like begin plus plus. So you can see, again, it's sort of a set local, get local, add thing that's happening here. And that's basically the whole thing. So then there's a return result at the end, and then that's your entire function. So then in WebAssembly, you also have to sort of, it's a contained module. Basically, WebAssembly will never do anything. It can't do anything to your JavaScript environment that you don't allow it to. Basically, you have to import anything you want to call, and you have to export any functions you want to make available to the environment. So that's what we're doing here. We have a memory that we're importing from outside, And then we have a function that we're also exporting outside. And so then all you get from your module, just like a JavaScript module, is all the imports and the exports. So this is kind of what the binary would look like. This is the actual binary. It's 80 bytes. Again, I love this stuff, but I'll move through it quickly because I'm running not too bad on time. So there's a little header here. Here you can sort of see the strings. There's that mymem and the sum. And then this is the function at the end. It's just the rest of this stuff is the function. Again, I won't go through the bytes. Nobody wants that. So then putting it all together, basically, this is like in Node, I ran this. It does work. Although someone's probably going to copy this from the slide and be like, you made a mistake. But basically, you can see here, like pretty easily, you can instantiate the memory, then just copy the data in like you did before. Then you create this import object saying which modules you want to import, and then you instantiate your WebAssembly object. Then you can call your export. That's what the instance export sum is. And then you can log the result. So a little bit more verbose than you would have with your JavaScript. But what you're getting out of this is sort of a separation between the imports and the exports. So using WebAssembly with Node, let's take a look at some of the stuff you can do. Some of the stuff that I tried out. So one of the things I wanted to try out was was Brotli. Brotli is really cool because it's this compression format. It's actually really popular on the web. People are using it instead of gzip because it usually gets a little bit better compression. And so I wanted to see what it was like. There's actually a number of Node libraries that do this already. There's Brotli.js, there's iltorb, there's actually a JavaScript implementation in the Brotli repo as well. And I wanted to see what a WebAssembly implementation would look like, so I decided to try it out. So here's the steps that I went through. Downloaded Brotli, just pulled it straight from GitHub. I compiled with Emscripten. I already had Emscripten set up, but it's actually really easy. If you just search for Emscripten, you can build it right away. Or you can just download it and get access to it. The few things that I'm doing here, Brotli is compiled with CMake, so I pass in a toolchain file, which basically says, instead of using your host toolchain, use Emscripten instead. That's all that's doing. Then you pass in this flag here, -s wasm. What that's saying to Emscripten is, generate WebAssembly code. And then finally, I say, build the release version of it. All right, so I do that, and I have some library files. And so the library files it generates are a decoder and an encoder, and then some common bit that's shared between the two. So if you look at the API for Brotli, there's this C function here. And it's pretty simple and actually gives you exactly what you want. You basically give it a buffer of data that you want to compress and a size. And then you give it another buffer, which is where to write the data. And then it'll give back the size of that compressed data. So basically, what I did here was I wrote a command which says, compile this library, and actually all it's doing is it's loading that library in, but export a function from the library. So this is a little bit of a voodoo. There's nicer ways to do this, but this is kind of like a simple sort of one-liner good for a slide. All I'm doing here is I'm saying, take these libraries, extract this one function, the function I mentioned before, Brotli decoder decompress, add in a little wrapper JavaScript, and then spit out a brotli.wasm JavaScript file. So that's what this bit of function is doing here. So then let's talk a little bit about the JS wrapper. So the JavaScript wrapper basically needs to be able to say, OK, I've got this WebAssembly module, and I've got this function that's being exposed, but it's exposed using those those types that I talked about before, right? I32, F32, I64, F64. It's not really the types you want to work with in JavaScript. What we want to work with is like a node buffer. So that's what I'm doing here, is I'm taking the encoded buffer, and in this case, I'm just saying I know what the decoded size will be. That's actually not too uncommon when you're decoding. And what I'm doing here is like kind of a pseudo-C JavaScript thing, which is a little bit funny. So you can see I have this _p after all the names. That's kind of like a pointer. So it's a pointer. It's more like an index into the WebAssembly memory. You can think of it as being like, where is my buffer in the, in the WebAssembly linear memory, like I described before? So what you can see there is I'm actually doing malloc, and this is the real C malloc. If you write C or C++, this is, well, you shouldn't be using malloc in C++, but this is the actual malloc, and this is the actual free. So I'm just allocating the buffers that I need, and then wrapping in a try finally and cleaning it up if anything goes wrong. So then I'm copying the data into the buffers. This is just standard JavaScript stuff here. There's a little bit of magic. You can see the module heap U8. That's something that's exposed by the wrapper code. It's basically the accessor into the linear memory. And what I'm doing is taking the encoded buffer, which is the node buffer, and I'm just copying the data directly into memory. The only other trick here is that I have to sort of write the size in, and so that's what that second part is doing. There's actually simpler ways to do that, but I'm trying to keep it as like no magic. This is like literally what's happening under the hood. It's just writing bytes into buffers. Finally, we call the function, passing in all the data that we created before, and then we copy the data back out. Right? So all that's happening here is we say, OK, well, we know the size of the actual decoded buffer. Then we copy the buffer back out. And then the node buffer API is a little bit weird. It actually aliases the buffer if you use buffer from. So then we just do buffer from again, and it makes a copy. And that's it, actually. That was the entire wrapper function for decoding. And so just to sort of, OK, I shrunk the font down a little bit. But this is 19 lines of code, basically, to do the wrapper for this. So this is the part that I was a little bit unhappy about. It's not as fast as the native bindings. It actually is pretty fast. So it's faster than the JavaScript implementation, both of the JavaScript implementations that I found. And there are some options that are not currently exposed to Node, but are actually going to be available soon after. That allow you to get some additional performance there. But you can see that the native bindings are still quite a bit faster, at least in this particular case. I will mention that I found that usually it's not this far ahead. I noticed that it's using SIMD actually in the native code. We don't have SIMD currently in WebAssembly, so that might be some of the discrepancy. So when we have SIMD in the future, these numbers might change quite a bit. But you can see it's actually pretty good performance. Like, we're getting 2x. So again, for this use case. So again, Benedict is probably upset with me about that. So the native bindings are quite a bit faster. Why would you use WebAssembly then? What's the benefit? Well, here's one thing that I'm super excited about. You compile once. You could drop your WebAssembly module directly into your package, and it'll work on any ISA, any VM, that supports WebAssembly, or any OS, right? That's pretty cool. You can use that same module on the web. So now you want to basically take that module and say, oh, I'm going to drop it into my client. Do it. It'll work. You can write the bindings layer in JavaScript. Like you saw, I wrote no C code. I wrote C-like JavaScript, but it's still JavaScript, and you can write your own wrappers for that. And there actually are some nice ones. And it's sandboxed, right? If you use the native module, well, you could basically scribble memory. You can do whatever you want. It's C++, right? This is sandboxed. You can't break it. If you broke it, you'd break your website, and we don't want that. So we're trying pretty hard to make sure that that doesn't happen. And you don't have to rewrite your C++ libraries. Like, a number of people already want to do this, right? They're taking libraries and they're rewriting them in JavaScript, right? Just take your C code, compile it to WebAssembly, and then you can drop it in, and you get access to it. I'll mention that I actually tried SQLite as well, and I got that running, and it was pretty simple to do. OK, so why are some of the reasons why you might not use WebAssembly? Well, we saw it's not as fast as native, and it never will be, because we're doing more work. We have more bounds checks. We have things that we're doing to try and protect you, and that's probably going to make it be a little bit slower. We have no direct access to native libraries. So if you want to basically access something like for the file system, you can't do it through WebAssembly. Like I said before, it's like it's an encapsulation. It can only access what you give it access to. So this is really about like speeding up computation. That's a big part of it. And there's no direct access to Node.js modules. Again, it's the same sort of thing. The WebAssembly module is kind of its own little universe. So here's some things that we're working on in the CG, the community group for WebAssembly, that I'm super excited about because I'm actually one of the champions for. So SIMD, like I said, some things to get some additional performance. Threads, which I know some people are very excited about, and some people are like, why are you doing this? But trust me, it's awesome. That's the one I'm the champion for. Zero-cost exceptions to make exception handling really fast. Host binding to make it so it's easier. So that binding layer, you might not have to write anything. That's what that feature is for. Tail calls, some people are very excited about. And then, of course, garbage collection, which will basically open the door to any number of new languages. And that one is further out, but I think definitely on everyone's radar. That's the talk. I hope you're excited about WebAssembly. And if you are, here's some of the links. And you can, of course, send me any questions on Twitter or GitHub as well. Thanks so much.